Hello, this is Rob Weber, CEO and co-founder of AgileSwitch. We're a manufacturer of gate drive boards and power stacks based on IGBTs, and we serve the renewable energy and electric motor industries. I'm here to tell you about our new product, the AgileStack Power Stack. It's the industry's first and only fully configurable power conversion module that features switch stream technology to control, protect, and monitor over 40 points of operating and fault conditions, as well as our new Stack Black Box technology to store onboard fault data in the event of catastrophic failure. In designing the stack, we've integrated best-in-class components from leading manufacturers of power electronic components, and we've configured the stack to operate in either DC-AC or DC-DC configuration. In fact, the same stack will operate in either configuration based on a software command sent from the controller. The power ratings range from 50 kilowatts to 125 kilowatts based on a heatsink. It can go higher with a chill plate. And overall, the system is highly configurable, primarily by software, to the specific needs of the application. What we've done is integrate in IGBTs. We're using the EconoDual platform. Shown here are IGBTs from Fuji in our standard product. Gate drive boards and interface boards developed by AgileSwitch. Current sensors from LEM. And heat sinks from Methode. They also provide the bus bars. In our kits, which we'll talk about a bit later, we also offer capacitors from SBE, featuring their new Power Ring film-based capacitor. What we're doing in the stack is providing a level of detail on fault conditions, monitoring, and reporting at a level never before seen in an IGBT-based stack. For each HB, or half bridge, in the system, and there are 3, we're able to provide data on DSAT, both high and low, UVLO, also both high and low, gate acknowledge high and low, and then for each half bridge on cross-latch shoot-through, DC link over voltage, over current, and over temperature settings. We're also monitoring real-time DC link voltage, current, and temperature, again for each half bridge. We do this based on our new patent-pending communication protocol, which serves as the backbone of the system. You can see here the 26-pin connector that both sends the trigger signals from the controller and also receives the fault and other monitoring information on the transmit and receive lines shown through lines 21 through 26. As mentioned, the system is highly configurable. So through software, you can adjust DSAT, UVLO, cross-latch shoot-through, DC link over voltage level, over current level, and over temperature levels as well. We've implemented a new bit of functionality, which we call Stack Black Box technology. What the Stack Black Box technology does is we capture the last 8 fault states in EEPROM. In the event of a failure, we are able to capture and store that information for later retrieval and analysis. To get you up and running quickly, we've partnered with National Instruments and have integrated in the National Instruments General Purpose Inverter Controller into the overall system with the AgileStack as shown here. We developed a breakout card to interface between the NIG PIC and the AgileStack, and the system also includes the SBE capacitor as well. And with NI, you do get an evaluation kit and evaluation software to be able to get a handle on the capabilities of the power stack as well as the NI system. A few additional key features of the AgileStack: differential or single-ended 3-volt trigger inputs. This allows high signal integrity over long connections to the controller. We did break out separate connectors for both trigger signals and power. We find this helps reduce system noise and errors. Switching frequencies for the IGBTs up to 15 kHz standard, and in fact can go higher, perhaps up to 30 kHz, with lower current rated IGBTs or water-cooled systems. We have manual reset by the host, and factory calibration parameters and settings which are available on request by the controller. These can be field modified as well. We have a 5 megabyte per second data rate, 3 14-bit current sensors at 200 ks per second sampling rate, 3 12-bit temperature sensors at 1 kilohertz bandwidth, 1 12-bit DC link voltage sensor also at 1 kilohertz bandwidth. We have a fault status byte with detailed fault information based on host request, and onboard factory set offset and linearity calibration parameters. The timing for when the A to D current sampling occurs can be configured for each half bridge, and it can either be a fixed time after each trigger occurs or initiated by a second pulse on the trigger line. Temperature and DC link voltage can be sent every sample or on request. Actions can be taken automatically or only upon a fault, and in-field calibration of current, voltage, and temperature sensors are possible with the AgileStack. Why did we put a separate power connector on when many systems on the market today tend to combine those? We found that supplying power over the same cable as signal causes additional noise and makes EMI shielding all the more difficult. Also, the limited number of pins on most standard connectors in the market today, on most stacks, don't allow for differential signals, and we feel this is also provides better noise immunity. And power supply distribution isolation is much easier to implement with separate power supply connector. That's our rationale. So how does the stack compare, the AgileStack compare to current stacks on the market today? Typical stack on the market today might have one or more of 5 potential events which essentially tell you that a fault happened. The AgileStack will tell you which of 40 potential faults actually happened. And of course that lets you drive the stack more efficiently, identify deteriorating conditions if they're occurring quicker, and for the first time start to do true analysis of catastrophic failures as well. In most stacks, temperature is monitored at one location, often that is only at the heatsink. We monitor at 3 locations inside of each of the half bridges, and of course temperature being the main cause of failure, this gives at least, we feel, 3 times the level of measurement precision. Development time for developing a stack today can be fairly complex. We interpret the information, the voltages in the stack, and present that as data points to the controller. This, along with the NI system, can dramatically reduce development time, at least by 25%, if not 50% or greater. Also, stack controllers tend to be fairly expensive. You need to put in expensive circuitry to protect against voltage spikes. We isolate the voltage levels at the stack, and that gives us the opportunity to provide clean signals to the controller. Again, driving down cost and complexity, and as noted, integrated very tightly with the NI GPIC system. What we're looking for is the future of improved communication, where data from advanced monitoring, augmented by predictive analytics, can help prevent and preempt system failure, and also adjust overall system performance in the field. This will enable extending the lifetime of the standard IGBT-based stack and therefore the inverter, and shorten development time while also improving supply chain management, given the ability to use on our part multiple sourced IGBTs. You can reach us at AgileSwitch.com. Email us at info@AgileSwitch.com as well. Call us in the US or North America, Europe or China, or send me an email directly, rweber@AgileSwitch.com.